Okay, so if I could have your attention to go through this. We talked yesterday about how to find what we call an integrated rate law. And then we were talking about the order. You can have a zero order, first order, or second order. And if I could just hide this for a moment, I'll go somewhere else on this screen. Hopefully it's not to a crazy YouTube thing. That would be a little distracting too. When we find the order of a reactant, the order doesn't tell how fast the reaction. If you have something that's second order, it doesn't mean it's a fast reaction. All the order means is how much does the concentration of that reactant affect how fast the reaction goes. It's kind of describing what does the reactant concentration do to the reaction. So if it's zero order, that means that the reactant concentration does not affect the rate. It goes fast or slow regardless of how much of that reactant you have. If it's first order, that means that the concentration of the reactant affects the rate to the first power. So if you double the concentration of the reactant, you'll double the rate of the reaction. That's what first order means. If it's second order, that means that the concentration of the reactant really affects the rate, so that if you doubled the concentration of the reactant, it would cause the rate to quadruple if it's second order. So that's all that order means. Now you have to figure out what the order is in order to be able to write an integrated rate law. The integrated rate law is a mathematical equation that describes how changing the concentration affects how fast it's going, or maybe it's the other way around. The rate law equation will tell us as time goes on how fast is the concentration going down of the reactant. Because the reactant concentration always goes down. We just start with some amount of it, and it makes products, and so it goes down. So you'll see some data tables with this. Oh, there it is. Okay, this is a summary of what we did yesterday. If you haven't written this down yet, this is a good thing to have, just so everything is right there together. If the reactant is zero order, you know that based on doing a graph. We talked about that graphing yesterday. If you just graph the concentration of the reactant versus time, and it gives you a straight line, that means it was zero order. And maybe I'll put the shade up, and we'll talk about this, although I don't have good luck with the shade.
Why does it turn?
One by one. Yeah, when I get close to it, I think, but don't touch it, it changes color. Yeah, like that.
Oh. If you just cover there, will it just like punch you color? It's like a disco party. There you go.
Now, if it's zero order, the integrated rate law for that reaction, assuming that the reaction is this, A yields products. So the reactant we're going to call A. If it's zero order, the integrated rate law would be this. Concentration of A equals negative KT plus concentration of A0. That's the equation that we would use to describe how fast that concentration is changing over time. Now, just to make it very clear, because yesterday was so much of a blur, the A0 term is the initial concentration. Hopefully you can read that. Initial concentration is A0. The K, remember what the K stands for?
The constant.
Yes, it's the rate constant. It's the rate constant that tells how fast the reaction is. If K is big, it's a fast reaction. If K is small, it's a slow reaction. The magnitude of that term right there is what we know of as fast or slow. So this thing right here is the rate constant. I try to write small, but everything blends together. Rate constant. Well, that's a mess. It's a T. I've covered up now part of my T. Yeah, and T's for time. A0. And A0 is the initial concentration. So over time, as the reaction proceeds and goes that way, the amount of A is going down. And if it's a fast reaction, the A goes down really fast. Okay? And that's determined by that K value right there. Now, we have a negative sign on that because K is the rate constant. It's a positive number. But as we monitor the concentration, it's going to be going down. We have a graph, it's going down because we're using up reactant. Asa, what you got?
Is that like KT?
It is K. I've covered part of it up. A equals negative KT plus A0. Okay. When it's first order reaction, that means the natural log of the reactant concentration over time is a straight line. So there's graphing that we have to do. When we do the lab on Monday, you're going to run a reaction. You're going to monitor the concentration versus time. We're going to use the spectrometer to tell us what the concentration is because we'll talk about the lab later on. But so our absorbance of light data is going to directly reflect what the concentration is. So we'll plot just the absorbance versus time to see what order the reaction is. Now, if we have a first order reaction, that means that the integrated rate law would look like this. Natural log of the concentration equals negative KT plus natural log of A0. Thanks. Oh, yeah.
Wait, why would it be straight again? Like one is 0, right? So it's like y almost like a number, right?
Say that again.
It's like, why is it a straight line again? Like what do you plug into?
Yeah, you would plot the natural log of the concentration at several different points versus the time. I'll show you examples of what that means. Plus ln of A0. And if it's not zero order and it's not first order, it's probably second order. So the second order reactant means that a plot of 1 over the reactants versus time. The inverse of the reactant concentration will give you a straight line. So the integrated rate law for this one would look like this. Now there's something a little bit different. It's a subtle difference. The subtle difference, anybody catch it? The K is positive. Right. In front of the K is positive. The K is always positive, I guess, but for the zero order and first order, you've got a downward slope. But if it's a second order change, as the concentration of the reactant goes down, its inverse is going up. So the second order graph is always going to give you a positive slope. Here's what we're going to do. I'm going to jump ahead. Are we good with that? Oh, go ahead. I'll wait for you. I want to show you an example, and I have done one where I went into Excel and I made the 3 graphs. This is what you'll be doing on Monday. Mm-hmm.
How long is this year?
Test on the 13th, so it's 2 weeks.
Wait, so we won't have a quiz for 2 weeks.
Deal.
Should we start doing the questions this weekend? Yeah.
Mm-hmm. Try some integrated rate law questions, yeah. They're not first. First are going to be the differential rate law. And you'll see some of these problems, what they look like, and we'll talk about it. All right, I'm going to skip this one for a moment. And I'm going to skip half-life. I want to go right to this. I'll come back to those other things. And I think I missed a page. No, I'm sorry, it was this one. Okay, take a look at this. In the book, this is number 43. Questions like this, where you're given time and concentration data, try a couple of those this weekend. Try to do them, look up in the solution guide how they're done if you can't figure it out, and see if you can get to the point of being able to do these and identify what order the reactant is. So this is up here, it's just describing what reaction they're talking about. Dimerization is when two molecules that are identical join together and become twice as big because they join together. That's making a dimer. Remember, if many add on to one another, that makes a polymer. So we start with one monomer. The monomer would be C4H6. Once another C4H6 comes along and joins to it, that would be a dimer, and then another one would be a trimer, and then you just keep going and you make a polymer from that. So that's all that means. It doesn't have anything to do with what we're going to try to answer in the question. So they give us concentration versus time data. And we're asked, okay, assuming that the rate is how that changes over time, determine the form of the rate law, comma, the integrated rate law, comma, and the value of the rate constant. Did they just repeat themselves? They wanted the rate law and then the integrated rate law. Here's what they were doing. If they say the rate law, it means the differential rate law. We haven't learned how to do that yet. So right now we're only working on the integrated rate law. So anytime you see rate law, for now, ignore it and just move on and see if you can find the integrated. So to find the integrated rate law, that's where we have to take the concentration versus time data and do the three graphs. So I did that. I took this data. There's 5 data points here of time versus concentration. And I made an Excel graph. Yeah, that was neat.
So fancy.
Oh. Okay, I love that. Sometimes you get lucky. Okay, so anyway, take a look at what I did up here. I have my 5 time points and the 5 values of the concentration that the problem gave me. So I did that first. Then I took those values of the concentration, took the natural log of them, so I could do the first order graph. And then I took 1 over the concentration, so I could do the second order graph. And I have the graphs over here. I'm going to bring them over one at a time. Oh, not the whole thing.
I don't think that's gonna work.
Man, on the other smart board, it works so nice.
Is this supposed to be the good smart board?
Oh, I hit that. No. Can I even make this bigger?
If you need to use like 2 fingers or something.
Yeah, maybe I'll just use the mouse.
Or you could just use that. Amber.
Yeah, why don't you?
Amber, stop it. I'm not that good.
No, but just.
Stop.
Okay.
What's easy for you is not easy. So I have a graph of the concentration versus time. If this is a straight line, that means that it's a 0 order reactant. Is it a straight line?
No.
Do you need to compare it to others to know whether it's a straight line or not? It's not straight. Okay? It's pretty much not straight. So I'm putting that away again. We know it's not 0 order. Daniel, don't try to guess.
What?
All right. Oh, look at this one. The natural log of the concentration versus time. What do you think of that?
It's,
Pretty straight. Yeah?
yeah.
But not perfectly straight.
Oh.
So maybe we ought to look at the second order graph as well. So we maybe have one that's in the running for the straightest graph. Don't say anything. Now, here's our second order graph, the inverse of the concentration. Notice there's a positive slope. Is that more straight than that?
Yeah.
Are you positive?
No. How do we figure out if it's straight line?
All right, so how do we figure it out? If you have 2 that look pretty similar and pretty linear, here's what we do. Now, watch carefully because you'll need to do this when you do this on